welcome to the Deep Dive. Today we're talking about something incredibly precise, almost, well, unbelievably so. The cutting tools needed for medical implants.
That's right. Things like hip joints, dental implants.
Exactly. Stuff where there's zero room for error.
Yeah.
It's machining, but at the extreme edge of difficulty.
It really is. I mean, the medical device industry is huge. Obviously, everything from simple tools to complex scanners.
Sure.
But we're zooming in on those parts that go in the body, orthopedic, dental. That's where the challenges really stack up.
Because they have to work with the body itself.
Precisely. The materials have to be strong, biocompatible, and the surface finish needs to be, well, perfect. It demands tooling that's way beyond standard engineering.
Okay, so let's sketch that out. If you had to list the biggest headaches for a tool maker here, what are the top three?
Number one, definitely the materials. We're talking titanium alloys, cobalt chromium, some very tough stainless steels.
Not easy to cut, I imagine.
Not at all. They're incredibly difficult. They generate a lot of heat. They're abrasive. They just wear tools down like crazy.
Okay, material difficulty. What's number two? The shape.
Exactly. The complexity. Think about a knee joint, the contours. It's not simple geometry.
Right.
Requires complex, multi-axis machining to get those sort of organic shapes right.
And the third hurdle.
Scale and precision. These parts are often tiny, the dimensional tolerances are incredibly strict, maybe just a few microns.
Oh.
And critically, as the sources really stress, the surface finish has to be absolutely flawless. Even a microscopic scratch could potentially cause problems down the line inside the patient.
It's amazing. So high stakes. How do manufacturers actually manage this? What kind of machines are we talking about?
Well, they rely on pretty advanced equipment. You see a lot of modern, high-performance multitasking machines, the small to medium-sized ones.
Okay.
But there's also a heavy reliance on really specialized machines, particularly Swiss-type lathes and lathes with live tooling.
Okay, pause there. Swiss-type lathe. For someone not familiar, what makes that different and why does it dictate the kind of tools you can use?
Right. So standard lathe holds the workpiece and the tool moves around it. A Swiss-type lathe is sort of the opposite, especially for long, thin parts. The workpiece, the bar stock, actually slides through a guide bushing, moving past stationary or moving tools. The cutting happens right near that bushing.
So the action is concentrated in one very small spot.
Exactly. It provides great support for slender parts, but it means the working area is incredibly cramped, super tight.
Which means the tools have to be?
Miniature. And highly precise just to fit and function in that restricted space. Purpose-built, really.
Okay, so the tools are tiny, and they have to cut those nightmare materials we talked about.
That's the core challenge. Designed for small parts, limited space, and tackling those ISO-S and ISO-M material groups.
ISO-S and M remind us.
ISO-S is primarily your heat-resistant superalloys, think titanium. And ISO-M covers stainless steels, including those tricky cobalt chromium alloys. The tool geometry, the coating, everything has to be optimized for those specific materials.
And this is where speed becomes a major factor, right? Small tool diameter means you have to spin it incredibly fast.
That's it, exactly. To get the right surface speed at the cutting edge with a tiny diameter, you need much, much higher RPMs. Rotary velocity goes way up.
So you can't just use any old machine.
Well, not just the machine. The tool itself needs serious consideration. It needs what engineers call a dynamic strength margin.
Dynamic strength margin. Sounds important.
It is. Basically, it means the tool has to be inherently strong and balanced enough to handle those extreme rotational speeds, tens of thousands of RPM sometimes, without vibrating itself to pieces or just failing.
So the speed requirement fundamentally shapes the tool design.
Absolutely. It's not an afterthought. It's baked in from the start.
Okay, so we've got tough materials, complex shapes, tiny tools, cramped machines, and the need for insane speeds. The solutions must lie in clever tool design. Let's start with turning those superalloys. Where's the first innovation?
Heat management, always critical, especially with titanium, which generates so much heat. Getting coolant exactly where it needs to be is key for efficiency, tool life, surface finish, everything.
So better cooling.
Yes, but highly targeted. We've seen real progress here. The sources highlight things like the Pico cut line for miniature turning.
And what are they doing differently? Just blasting more coolant?
No, much smarter than that. They're building coolant channels into the tools themselves. So you have inserts with tiny holes delivering high-pressure coolant right at the cutting edge, literally fractions of a millimeter away.
Internal channels.
Yes, internal channels in the holders, getting the coolant precisely to the heat zone. And they've done this while keeping the clamping systems user-friendly and really really stiff.
Okay, that tackles the heat. But what about rigidity? You mentioned vibration is bad. How do you clamp that tiny insert so firmly it can handle high cutting forces without moving?
Right, that's crucial for productivity. We're seeing new square shank holders, especially for Swiss type and standard CNC lathes, using advanced clamping mechanisms. The sources mention the safe T-lock mechanism as a key example. It provides incredibly precise and extremely rigid mounting for the insert.
And that rigidity translates to
Better performance. You can push the cutting speeds and feeds higher, get better productivity, and the tool lasts longer, even when you're machining really tough stuff like cobalt chrome. Combine that rigidity with the high-pressure coolant option, and you see real gains.
That makes sense. Rigidity equals speed and tool life. But let's talk cost. These materials, titanium, cobalt, chrome, they're expensive, right? Every sliver of waste must hurt the bottom line.
Oh, absolutely. Material cost is a huge factor. So minimizing waste is critical for profitability.
Where does tooling help there?
A big area is in parting off when you cut the finished part from the bar stock. Traditionally, that cut creates a fair bit of waste material.
Okay.
So the innovation is to make that cut much, much narrower. We're seeing new compact tools using things like self-group heat inserts that come in incredibly narrow widths.
How narrow are we talking?
Down to maybe 0.6 millimeters, up to maybe 1.2 millimeters, really slim.
Less than a millimeter wide cut.
Exactly. For parting off bars, say up to 16 millimeters or so in diameter, it saves a surprising amount of that expensive material on every single part, especially valuable on those Swiss-type machines running costly bar stock.
0.6 of a millimeter. That sounds incredibly fragile, though. Doesn't a tool that thin just want to wobble or break?
Ah, good point. It absolutely increases the risk of vibration or deflection, which brings us right back to rigidity.
Right. The clamping.
Precisely. You can only get away with such a narrow parting insert if the clamping system holding it is exceptionally rigid and stable. It's all interconnected. The slim profile demands advanced clamping to work effectively and reliably.
Okay, so we've tackled turning, rigidity, material saving, and parting. Let's shift now. Many medical parts aren't just simple cylinders. They have holes, complex curves. Think hip stems, knee components. Let's talk drilling first.
Right. For drilling holes in these components, small, solid carbide drills are, well, pretty standard.
But expensive, I assume. Solid carbide usually is.
Yes, they perform well, but the cost can be high, especially when you use a lot of them. An alternative is assembled drills with exchangeable cutting heads.
So you just replace the tip.
Exactly. You replace the small carbide cutting head, not the whole steel body of the drill. Much more cost-effective in the long run.
But there's a catch.
The challenge has always been miniaturization. Making those exchangeable head mechanisms work reliably at very small diameters is mechanically quite difficult.
How small are we talking? What's the barrier?
Well, historically, these assembled drills were mostly for larger holes. But the sources point to a breakthrough with drills like Iscar's SumoCam. They've managed to shrink the technology down.
Oh, yeah.
They recently reduced their minimum diameter for these exchangeable heads from 6 millimeters down to 4.5 millimeters.
Well, that doesn't sound like much, but I guess in this world.
It's significant.
Yeah.
It opens up that cost-saving potential to a whole new range of smaller medical parts that are often made in high volumes. It's a big deal for manufacturers.
Okay, so drilling is getting more cost-effective even at smaller sizes. Now, what about those complex surfaces? Getting that perfect smooth finish on a curved shape, like the ball of a hip joint. What's the standard approach?
Traditionally, the main tool for that kind of fine milling or contouring is the ball nose end mill.
Right, shaped like a ball on the end.
Exactly. It gives you a nice point contact, which is good for complex curves. But there's a major drawback.
Which is?
To get that perfectly smooth, high-quality surface finish required for implants, you have to use a very, very small step over between passes. Tiny steps.
Ah, so the point contact means you need millions of tiny overlapping passes to smooth it out.
Pretty much. You have to drastically reduce the step size, which means many, many more passes over the surface.
And that means?
Cycle time goes through the roof. It takes forever to finish the part, which is incredibly inefficient, especially on expensive multi-axis machines.
So that's the bottleneck. What's the solution? How do you get the finish without taking all day?
The advanced solution is the barrel-shaped mill, sometimes called segment mills or circle segment cutters.
Barrel-shaped. How does that work?
Instead of a small ball radius, They use a cutting edge based on a very large radius, like the curve on the side of a barrel.
Okay.
When you tilt the tool slightly, that large radius engages the surface over a much wider area compared to the point contact of a ball nose.
Bigger contact patch.
Exactly, which means you can use a much larger step over between passes.
And still get the same smooth finish.
Yes, or often even better. It's particularly effective in 5-axis machining for those complex orthopedic shapes, like knee components.
Is this a minor improvement or a major one?
Oh, it's significant. We're talking potentially dramatic reductions in cycle time. Hours can sometimes be shaved off complex parts. You get much smoother surfaces, fewer passes, much higher productivity. It's a real efficiency driver for machining titanium, those exotic superalloys, stainless steel.
Okay, that's a clear leap forward for contouring. Let's circle back one last time to machine limitations. We said small tools need high RPMs. What if your machine just can't spin that fast? Maybe it's an older machine.
Yeah, that's a common bottleneck. You have the perfect small diameter tool, maybe for fine milling or engraving, and it needs, say, 40,000 RPM to work efficiently.
Right.
But your machine's main spindle only goes up to maybe 15,000 or 20,000 RPM. You're stuck.
So what do? Buy a whole new machine?
Not necessarily. There's a clever solution. Specialized spindles driven by the machine's high-pressure coolant system.
Driven by the coolant, like a water wheel.
Sort of, yeah, like a miniature turbine. Brands like Microns 90 are known for this. They take the high-pressure coolant flow that's already there for cooling and use that hydraulic energy to spin a very small, high-speed spindle independently. The main machine spindle just sits idle.
Wow. So it's like adding a turbocharger just for the tool.
That's a great analogy. It lets you achieve speeds in the range of, say, 35,000 up to maybe 53,000 RPM, even on a machine that can't normally hit those speeds.
Solving the speed barrier for things like fine milling, drilling, deburring.
Exactly. It allows manufacturers to use the optimal cutting speeds for these small tools without needing a massive capital investment in ultra-high-speed machines across the board.
Okay, so putting this all together, the focus on tricky materials, the coolant innovations, the rigidity, the move to barrel mills, these coolant-driven spindles. What is this intense focus on optimizing cutting? Tell us about where the medical device field is heading.
It tells us that constant rapid evolution is basically the norm. The medical industry is growing fast, and it's always adopting new materials. We're seeing more composites now and new technologies like additive manufacturing, 3D printing.
Right.
And these changes aren't just for implants. They affect surgical instruments, diagnostic equipment, tiny micromachine devices, everything. Tool manufacturers have to keep innovating just to keep up with the new demands these materials and processes create.
This has been a fascinating look into a really demanding manufacturing world. We've covered the tough materials like titanium and cobalt chrome, the critical need for tiny tools and perfect finishes, the clever solutions for cooling and rigidity.
Yeah, and the shift towards things like barrel mills to drastically cut down cycle times on complex parts.
And even ways to boost speed on older machines using things like those Microns 90 spindles. It's all about pushing the limits of precision and efficiency.
Absolutely. And looking ahead, that pace isn't slowing down. So here's maybe a final thought for you, the listener, to consider.
Okay.
Given how quickly composites and 3D printed parts are becoming more common in healthcare materials that don't behave like traditional metals, they don't form chips in the same way. How might this intense focus we've discussed on high-speed rotational cutting need to pivot? What new cutting or shaping methods might become essential when you can't rely on the physics of making a chip anymore?
Thanks for joining us for this structural exploration.
Absolutely. Catch you next time.